Assalamualaikum warahmatullahi wabarakatuh, and hi to my students. Right now for this video lecture, we want to investigate to check whether Zn binary operation and be any binary operation. We have Zn star special group of Zn and also unitary group of n. We need to check whether these three satisfy group properties based on certain binary operation. We start first with the case of Zn Z4 plus. To recap, we have four properties to define a group. The first one is closure. For every element in the given group, A binary operation with B will produce C. This C must also be in the same G. For associative, quick recap. For every three elements of G, A binary operation B, you do the front first, will be equal with, you don't need this. For the third one, identity, there exists some E for every element in G. There exists identity in the same G such that AE equals to EA, you get back A. For inverse, for every element in G, there exists an inverse in the same G such that A inverse is equal to inverse binary operation A, you get back the E. If you satisfy these four, then it is known as a group. If you include one more, which is commutative, for every element AB in a G, AB equals to BA. To satisfy these all five, then it is also a group, then it is also an abelian group. Okay, we already covered that on the previous video lecture, and how to apply in the case of Z4 plus. Z4 integer from 0 until 3. And in order to determine whether this Z4 under addition is a group or not, we need to have a Cayley table. There. Now we check the properties one by one. For the close, we need to identify the binary operation from this part with the elements from this part will produce something inside the Cayley table. You take any elements from Z4, you binary operation with the Z4 as well, A, B, will produce C. The C will is produced inside this Cayley table. And if you want to answer the closure, you must have a correct Cayley table first, and it's enough sufficient for you just to say based on this Cayley table, all elements based on the Cayley table produced, all elements is in Z4. What I meant is that the element here produced is the C. Is all the elements produced inside there is actually in Z4. You see 0 there, 1 is the element of Z4, 2 and also 3. So it's sufficient to mention only this statement. However, please be concerned that your Cayley table must be correct. If your Cayley table is wrong, then what you wrote here is not follow through. About associative, let me show you an example how to demonstrate first. It's not the correct proof anyway, because this must be for every 3 integers inside there. But if you want to include every kinds of combination between those 3 integers, it will be quite lengthy. This is what I meant. For example, if I take 0 binary operation with 1 with 2, you take 0, 1 first here. 0 plus 1 mod 4 becomes 1. And then binary operation with 2, 1, 2 here. It will become 3. 3 mod 4 is 3. You get 3. If you do 1, 2 first, you will get, you will refer to the table, 1, 2, you get 3. And then 0 plus 3, 3 mod 4 is also 3. What I can conclude by this as a example is that actually 0, 1, 2 is equivalent with 1, 2. There exists some kind of associativity there, but in order to represent for every 3 integers, you take 0, 1, 2, or 1, 2, 3, 2, 2, 2, 2, 2, 3, there will be many combinations. It's sufficient for you to say that it's not based on Cayley table, based on the properties of integer, because we know that integer, addition of integer is actually associative from the previous video lecture, and it also applies for the case of plus modulo n. Based on the properties of integer, which is also applicable to plus mod n, which is an integer as well, you can actually mention based on the properties of integer, addition, Z4 plus also is associative. This is the best answer that can summarize for every 3 integers. You don't need to show for every possible 3 combination. It's sufficient for you just to say this statement. Okay. Let's try to look for the third one, which is about the identity. Is there exists identity inside here? Identity, again, it means for every element inside in this Z4, there exists some identity in also in Z4 such that this happen. A, E equals to E, A, you get back A. So you take 1, for example. You take 1. Is there an element of E such that 1 E equals to E 1, you get back 1? And it must not also applicable for 1, it must also be applicable to 0 through 2 and 3 as well. And for the existential kind of proving, you must mention what are the E here. When you found out it is, for the case of 1, it is 0, because 1 plus 0 is equivalent with 0 plus 1, you get back itself 1. So for this case, the identity which is applicable for every element in Z4, E is equivalent to 0. My conclusion is that identity exists. There's one more way for you to see this. My tips to you is that the identity for plus addition is always 0. And you can also see from the Cayley table for this first row and also the first column, it will produce back the same value as the leading row and also the leading column. For the case of multiplication, the identity is always 1. But it depends on the group as well, of course, if it exists or not. When we have this identity, then we can check whether it has inverse or not. For the inverse, right now we lock the value of E there. Okay, E is 0. For the case of inverse, same goes for 1. It must mean that for every A in this G, there exists its inverse. It's also in the same G, such that A inverse is equivalent A, you get back E. Right now we know our case is E is 0. You take an example first. I want to show. For example, if you take 1, does exist the question, the inverse of 1 such that it get 0? Because from the previous step, the identity is 0. From this Cayley table, you need to read one binary operation with what? You get 0. In this case, as you can observe here, 1 binary operation with 3, you get 0. Same goes if the inverse 3 with 1, you get 0 as well. For the case of existential, again, I need to mention for every possible inverse. It means what is the 0 inverse? What is 1 inverse? We already know, which is 3. You must do that for every element inside Z4. Again, for the case of 0 binary operation with the inverse, you get back 0. Based on the Cayley table, it is 0. For 2, it's 2. And for 3 inverse is 1. It's quite interesting to note that the inverse of 1 is 3, the inverse of 3 is 1 back. It's kind of like an inverse function. For 2, it's itself. For 0, it's itself. So we already have proof that Z4 under addition satisfies 4 properties of a group. The last conclusion for the case of the question, is it a group or not, determined by checking all the properties. I can guarantee right now, based on these 4 statements, is a group. Now, while we're having at it, why not we directly determine whether it is a abelian group or not? Abelian, it must satisfy commutative. So for the commutative, it means for every 2 elements in G, A binary operation B equals to B binary operation with A. Again, for every, you have many combination 0, 0, 0, 1, 0, 2, 0, 3, and then you proceed with 1, 1, 1, 2, 1, 3, 2, 1, 2, 3, 2, 2, 2, 3, and 3, 3. There are many ways, many combinations. For this case, I can show you the example only first. For example, 1, 2, When you read from the table 1, 2, you get 3. 3 mod 4 is 3. 2, 1 is 3 as well. For this small example, it's conclude that 1, 2 is commutative with 2, 1. And you don't need to show for every possible combination out there. Again, for this kind of commutative, based on the properties, because we know that addition of integer is commutative. This is a well-known fact, well-known properties. Based on properties of integer addition, Z4 under addition is commutative. Okay, I can also accept this kind of answer based on Cayley table, because based on Cayley table we can also see that Z4 is commutative, but I prefer the first answer anyway. It's better, it's more precise than the second one, but it's an alternative. Z4 is a group and it's also commutative. If it is a group and it's also commutative, right now Z4, I also managed to prove to you that it is an abelian group. We do another example, one more. This time I want to involve a small one first, which is U4 under multiplication. Determine whether it is a group or abelian group. Again, U4 consists of an integer greater than or equal to 1, which is relatively prime with n. For this case, which is relatively prime with 4, up until an integer which is less than 4. So U4 consists of 3, and this time you need to do a Cayley table to represent the multiplication part. 1, 3, 1, 3. 1 times 1, 1. 1 mod 4 is 1. 3, 3. 3 times 3 is 9. 9 mod 4 is 1. Sufficient. Is it close? Based on Cayley table, it is close. Is it associative? Again, we have several combinations inside, and it is sufficient to say that based on the properties of integer multiplication, this U4 also is associative. Nothing interesting at this point yet. For the case of identity, what is the identity? You must mention, for example, I don't want to show the example anymore, we already said it. You take 1, you binary operation with E, is equivalent to E binary operation with 1, you get back 1. For this case, the identity for every elements inside U4 that behaves in that way for 1 and 3, the identity exists, E is 1. For the inverse, what is 1 inverse? Inverse, huh? One inverse that you such that you get back 1. One binary operation with the inverse, you get back 1. It is 1 itself. For the case of 3 inverse, it's 3 itself. The inverse exists, and based on this summation working, we can conclude that U4 under multiplication is group. For the question, is it commutative? Is it an abelian group? You need to check for all the 5 properties. And again, you can enough to say, and based on the properties of the integer multiplication, you know that multiplication is associative. A times b equals to b times a. A times b mod n also is equivalent with b times a mod n. And you don't need to show for every, it will be quite long. Based on the properties of integer multiplication, it is also an established well-known fact that U4 under multiplication is commutative. And as my last conclusion is that U4 is also abelian group. In my online lecture, maybe perhaps I will show you the example for subtraction, maybe if we have enough space there, enough time, sorry. But if you think about subtraction is not commutative anyway. In order for you to develop a Cayley table, you will find some problems. You can try to attempt to do it, but it will be not commutative there. You can try to attempt to do those for subtraction and even for division as well. But for the final outcome, it is not a group for plus and also for subtraction and also for the division. If you try to develop Cayley table, then you will have a problem. Try to do it first. I will demonstrate if you want to in my online lecture later. For the time being, this is enough for this section to prove the group an abelian group for the case of any Zn star. I don't show, but it's the similar principle with Zn and also Un, because it's still integer modulo n. The difference between those 3 is what the elements of integer inside the set only, but the binary operation remains the same. You plus, you multiply, and then any binary operation, then you mod n. There you go. See you in the next video lecture. Goodbye.